So, today we will discuss the structure of ionic solids. We have already discussed structure of metals. So, we have discussed metals. So, metals metals have metallic bonding. If you look at it in terms of bonding, we have not talked about bonding in any detail, just for reference. So, metals have metallic bonding. Then we discuss the structure of carbon in form of graphite, diamond, nanotube and fullerene. Carbon is a typical element to represent covalent bonding. Covalent bonding. We have not yet discussed anything which is ionically bonded. So, that will be the topic of this presentation. So, let us look at ionic solids. So, the difference here you in the metallic bonding was non-directional. This is what led to remember close packing. Since it is non-directional, you can pack as closely as possible. Whereas in covalent bonding, the carbon structures were not close packed because they are strongly directional. Directional bonding, and by directional bonding we mean, if you remember, that the bond angles are fixed. So, you can't do close packing because you have to keep bond angles fixed. For example, in diamond it was the tetrahedral bonding. In the diamond it was tetrahedral bonding. Tetrahedral, which means around one carbon you can place only 4 other carbons, whereas a close packing would have allowed, if you remember, close packing would have allowed 12 atoms around a given atom, but diamond demands only 4 around itself because it will not accept anything other than the tetrahedral bonding. So, now let us discuss ionic bonding in this slide. So, ionic solids. They are made up of cations and anions. Cations are attracted to cathode, so they are positively charged. The anions are attracted to anode, so they are negatively charged. Because of the positive, to get the positive charge, they lose electrons. So, usually their size, let me call it R cation, radius of the cation, and R anion, the radius of the anion, and usually cations will be smaller in size than anion, because anion is gaining electrons. So, it may add extra orbitals to gain those electrons to form anion. So, the size will increase, whereas cation, if you have 1 or 2 electrons in the outer shell and it loses that, so then it may lose 1 whole orbital. So, the size will reduce. So, cations are usually smaller than anions. This is an important fact when we want to contrast this with the metallic structure, because the metallic elements, all atoms were of equal size, but here now we have to think about ions of different sizes. We can again model cations and anions as spheres. Cations and anions as spheres. Also, there will be electrostatic attraction between cation and anion. So, they will like to come close together. So, they will like to come close together. So, this will also be, we can model the structure as close packing of these spheres. So, this also indicates close packing. However, because of this inequality in the size, this is close packing of unequal spheres. Also, it cannot be a totally random packing, because cations will like to be attracted to anions and anions to cations, whereas anion will repel and cation will repel. So, any given cation prefers to be surrounded by anions. So, around a cation you have a cage of anions. So, means if I try to draw schematically, if I have a cation, then it will attract anions around it. This is small cation, large anion. Now, anions also are repelling. So, they will like to maximize this distance. This is repulsion, whereas obviously there is attraction between anion and cation. So, they are as close as possible. So, the structure, the way the structure is modeled is to think of a close packing of anions and let cations sit in the voids. Now, it will not be exactly close packing, because remember we are saying that there is a repulsion, we are saying there is repulsion, and we are also saying close packing, which means they will be as close as possible. So, because of this repulsion, this close packing will be not exactly close packing, but something like close packing. So, anions can come close, but they need not be necessarily touching. So, let us mark that close packing, but not necessarily, not like metal, not necessarily touching. So, let us look at start with a very simple anion cage, and that is a triangular cage. Let's call this anion cage. So, a triangular anion. By this I mean that I will take my anions sitting on the vertices of an equilateral triangle. And let me introduce a very small cation there. So, it is not even, so anions are touching, you can see anions are touching, anions touching, whereas cation and anion are not touching. Not touching. So, which means this is exactly opposite of what we want, because anion there is a repulsion, but they are very close, and whereas cation anion have attraction, but they are not so close. So, this is not a favorable situation. So, we label this as not stable. Not stable. Let me then consider the next case where it just fits in the void. Cation just fits in the anion void or anion cage, I was calling it, touching all the surrounding anions. So, cation and anion touching, there is an attraction and they are touching. So, that is good, we have minimized the distance. So, at least we have achieved some more stability than what we had discussed here, because now cation and anion are in contact, whereas still we have not achieved a separation between anion and anion, which is not good from electrostatic energy point of view. So, this we will call critically stable. It is little better than not stable, but actually it is still not fully stable. And now, in the third case, let me try to make a really comparatively large cation which forces the anion out of contact. It forces the anion out of contact. This is a very good news, this is a stable, I will call this stable, because now the ions which are attracting are as close as possible because they are touching, and ions which are repelling have also been separated out. So, this will be the stable situation. So, which means I can think of a radius ratio, I can think of a critical radius ratio for stability of ionic structures. And what is that critical? We have already seen that, let me draw it again, we have already seen that in a situation like this, where the central cation just touches the outside ion, this is the critical situation. Critically stable. and what we really want to make it stable make the cation still larger, so that anions are separated out of contact. So, this is what we called stable. So, we can easily solve the geometry of this. This is an equilateral triangle, and this is the distance of the centroid to the corner of the equilateral triangle. So, centroid to corner distance should be R cation plus R anion. Whereas the edge length of the triangle is equal to 2 times R anion. This is 2 R anion. And then if you use the geometry of equilateral triangle, you can find the ratio of R C to R A. I leave this as an exercise to you to do. If you do that, what you will find that R C by R A for this critically stable structure comes out to be 0.155, which means for a stable structure we will need R C by R A to be greater than 0.155. So, for a stable structure it should be greater than 0.155. So, please do this as an exercise, a simple geometrical exercise. So, which means if we now consider, this is what we call a triangular coordination of anions around cation. So, this was the triangular coordination, and for triangular coordination we found that the stability requires R C by R A to be greater than 0.155, equal to 0.155 the critical situation. So, we include that also. What will happen if the radius ratio is less than this? So, then the triangular coordination is not stable. So, maybe you will have a linear molecule. So, R C by R A less than 0.155 will imply linear structure, that is the coordination number of 2. The cation will prefer to have only 2 anions. So, if you now think, if you then this was a planar case and it was in 2D, but the structure will obviously be 3D. So, if you come to now 3-dimensional structure, and think of the next higher coordination number. So, that is 4. 4 coordination or tetrahedral coordination. Of anions around a cation. This geometry we have already done when we were discussing close packed structure. We came to tetrahedral voids. We said that four atoms can be sitting on the vertices of a tetrahedron. In this case, they will be anions and there will be a central cation. And if the anions are touching, if anions are touching, you have already found what is the largest cation which can sit in. So, and that ratio let me now write it as cation anion ratio Rc by Ra is equal to, we remember it was 0.225. That was the largest sphere which can fit into a tetrahedral void. We derived this as a close packed structure. Review that derivation, you should be able to do this. So, for critically stable, so for critically stable tetrahedral coordination, this will be the situation. The stable tetrahedral coordination, again following our argument from the triangle, because in the critically stable one, anions also will be touching. We have allowed anions to form a close packed structure. So, anions also are touching, but we do not want anions to touch. If you do not want anions to touch, Rc should be larger than this critical value, because then it will open out the tetrahedron and will force anions to separate, and forcing anions to separate because they are like charged is a good thing. So, actually stable structure for tetrahedral coordination will require a value larger than this. So, by the same argument, if we now write Rc by Ra greater than 0.225, this will imply tetrahedral coordination. And you can include equal as a critical stability. So, stable tetrahedral coordination. So, now what you have, you got the ratio 0.155 for triangular, you are getting a ratio 0.225 for tetrahedral. If you put these two together, you will get both the upper and lower bounds for triangular coordination. So, if Rc by Ra, is less than this value 0.225, then tetrahedral coordination will not be stable. 4 anions will not be able to surround a cation. So, less than 4 is possible, and we have less than 4 is 3, and for 3 we have already seen that it should be greater than equal to 0.155. So, for triangular coordination we have found both the upper and lower bounds by this analysis. So, you can carry on this analysis for other coordinations. So, for octahedral coordination, remember the octahedral voids, octahedral which has 6 vertices. So, 6 anions will be there. So, octahedral coordination will require an RC by RA. I am now writing it quickly without much discussion, because I am just reminding you of the octahedral void in cubic closed packed structure where we did this calculation. So, it comes out to be 0.414. So, for a stable octahedral coordination it will be 0.414. We never discussed a cubic void, but you can think of a cubic coordination. That is 8 anions around a cation, and if you do a calculation you should be able to show that RC for RA for this will be 0.732. We never discussed a simple cubic void, but you can imagine one, that if you make a cube and place atoms on all the corners of this cube, something like this, then what will be the largest sphere which will be able to fit in the cubic void that is at the center of the cube, and that number will come out to be 0.732. So, for cubic coordination RC by RA, again for RC by RA 0.732, anions will be touching, and if you want for them not to touch, then you can increase the radius ratio. If it is larger, then the cation is larger and will force open this cube and anions will not be touching. So, for cubic coordination the number is 0.732. And finally, trivially, to just close this discussion, we can write for close packed coordination, let us say, that is the maximum possible, that largest number of spheres which you can give around a given sphere is 12. So, in this case all are equal spheres. So, that means cation and anion ratio should be equal to 1, which will hardly be the case, but from geometrical point of view we can write. Yes. So, let us summarize what we have said till now in terms of radius ratio and coordination number. So, let us have a column of radius ratio and let us have a column of coordination. And now, what we have seen, that if you have radius ratio RC by RA, RC by RA less than 0.155, then you have a coordination of 2, or what we call a linear coordination. The next critical value of RC by RA is 0.225 greater than equal to 0.155. This gives you 3 triangular coordination. We are just summarizing what we discussed in the previous slides. So, we are just rewriting everything in a single table. So, if you have greater than equal to 0.225, but less than 0.414, then you have a coordination of 4, and that is tetrahedral. And then when you have 0.414, 0.414 to 0.732, you will have a coordination of 6, which is octahedral. And from 0.732 to 1, you will have a coordination of 8, which is cubic. So, this table summarizes what we have discussed about the structure, and it tries to predict, essentially what it is trying to do, this table is to predict the kind of coordination which you expect simply on the basis of radius ratio. So, this will not always be, you do not take this as some sort of fundamental law or which has to be always true, but it is a kind of rough prediction based only on the geometrical size of the cation and anion. You know that the crystal structure or the bonding is a much more complex and many more phenomena happens, but this is a simple geometrical formulation which helps us in predicting the coordination number according to just the size ratio of cation and anion. One thing which sometimes causes confusion to students. So, let us look at the tetrahedral coordination. We find that 0.225 is the minimum radius ratio at which the tetrahedral coordination becomes stable. But this same number we derived when we were studying the cubic closed packed structure, the same number we derived as the maximum size of a sphere which will fit in the tetrahedral void. The two facts are not consistent, because that was our argument for deriving radius ratio for tetrahedral void, but sometimes it creates a confusion that whether this is a minimum or maximum for tetrahedral coordination. So, 0.225 is the maximum sized sphere which will fit in a tetrahedral void in cubic or hexagonal closed packed structure, but it is the minimum radius ratio at which the tetrahedral coordination becomes stable. Same argument goes for 0.414, it is the largest sphere which will fit in a tetrahedral void in closed packed structure, but it is the minimum ratio at which the octahedral void becomes stable. So, with this we finish this session. We will have another session on ionic solids, where we will look at the application of these radius ratio to some real structures.